Imagine oceans larger than Earth's, hidden beneath thick shells of ice, warmed not by sunlight but by the gravitational embrace of giant planets. This is not science fiction. This is reality deep within our own solar system. Beneath kilometers of ice on moons like Europa and Enceladus lie vast bodies of liquid water, called alien oceans, and they could be among the most promising habitats for life beyond Earth. Europa, one of Jupiter's largest moons, is cloaked in a fractured shell of ice. Its surface glows with lines and ridges, evidence of stresses and shifts in the icy crust. Below this shell is a global ocean, potentially up to 100 kilometers deep, more than 20 times deeper than Earth's oceans. The evidence comes from spacecraft observations, including Galileo's magnetic field measurements and surface geology, which together point to a salty, global ocean beneath the ice. Not far away, around Saturn, lies Enceladus, smaller but equally fascinating. Cassini spacecraft discovered towering plumes of water vapor and ice grains shooting out from fractures near its south pole. These plumes contain not just water, but organic molecules and salts, suggesting hydrothermal chemistry at work deep beneath the icy shell. Unlike Europa, where the ocean remains hidden, Enceladus actually spits samples of its ocean into space, offering a direct way to study its chemistry. These hidden seas are not warmed by sunlight. At the distances of Jupiter and Saturn, the sun provides only a fraction of the energy that reaches Earth. Instead, the heat comes from tidal forces, gravitational flexing caused by the massive planets and other moons. As Europa and Enceladus orbit, their interiors are squeezed and stretched, generating internal heat that prevents their oceans from freezing solid. This tidal heating is the substitute for sunlight in these distant worlds. The concept of an ocean beneath ice challenges our intuition about where life might exist. On Earth, life as we know it depends on sunlight, but beneath the frozen surfaces of these moons, life, if it exists, would rely on chemical energy, heat, and nutrients from rock-water interactions. These are environments where energy is available and water is stable, two foundational requirements for life. Humanity has long imagined oceans under alien skies, but Europa and Enceladus bring that possibility into focus. Their hidden seas are not merely curiosities, they are targets for future exploration. Missions planned for the 2020s and beyond aim to probe these oceans more deeply, using ice-penetrating radar, plume analysis, and high-resolution imaging to understand their habitability. In this series, we will explore how these oceans work, why they could host life, and how scientists model alien ecosystems in places nothing like our own. From icy crusts to hydrothermal vents, from organic chemistry to potential life forms, the secret oceans of Europa and Enceladus represent some of the most profound and exciting frontiers in astrobiology. Here, beneath the ice, the universe may be whispering answers to one of humanity's greatest questions. Are we alone? Jupiter looms large in the sky above Europa, but the real story lies beneath the moon's icy shell. Europa's surface may appear serene at a distance, a smooth, whitish sphere marked with cracks, streaks, and ridges, but this exterior hides a dynamic world beneath. Scientists have pieced together evidence that Europa harbors a global ocean of salty water, insulated under a thick layer of ice. The first clues came from NASA's Galileo mission, which orbited Jupiter in the 1990s and early 2000s. Instruments detected changes in Europa's magnetic field consistent with a conductive layer beneath the surface, most likely a salty ocean. Later observations from the Hubble Space Telescope hinted at plume-like activity, suggesting the ocean might occasionally vent material through the ice. Europa's ice shell is not uniform. Some regions may be tens of kilometers thick, others much thinner. Tension fractures and surface chaos regions point to areas where the ice is active and likely exchanging material with the ocean below. This means that Europa's ocean is not isolated. It may interact with the surface. Cycles of ice formation and melting potentially shuttle chemicals between worlds. The ocean itself is kept from freezing by more than just internal warmth. The tidal gravitational pull of Jupiter and neighboring moons, especially Io and Ganymede, flexes Europa's interior as it orbits. This constant gravitational tug-of-war generates heat through friction, warming the interior and maintaining liquid water. This process is analogous to wringing a wet towel, generating heat through motion. Tidal heating is the vital engine powering Europa's ocean. The composition of that ocean is another intriguing factor. Salts have been detected on the surface ice, and models of the moon's formation suggest the ocean is likely rich in magnesium sulfate and sodium chloride, making it more like Earth's salty oceans than a pure water layer. In astrobiology, salt is important because it supports the transport of ions and nutrients, which can facilitate chemical reactions essential for life. Understanding the chemistry of Europa's ocean, especially how it interacts with the rocky mantle underneath, is critical. If water interacts with rock at high temperatures, hydrothermal vents could arise, similar to those on Earth's seafloor. On Earth, vent ecosystems thrive without sunlight, relying on chemical energy from minerals and heat. If similar processes occur on Europa, they could create habitats rich in energy for life. The prospect of saturating this alien ocean with the building blocks of biology, water, energy, and chemical gradients makes Europa one of the top candidates in the search for life beyond Earth. In the next parts of this series, we'll look deeper at how Enceladus compares and how scientists model what life might look like beneath these hidden seas. While Europa's ocean remains largely concealed beneath ice, Saturn's moon Enceladus gives us tantalizing glimpses of its interior. In 2005, NASA's Cassini spacecraft made a discovery that transformed our understanding of icy moons, towering plumes of water vapor and ice particles erupting from fractures near the moon's south pole. These plumes, shooting hundreds of kilometers into space, offered the first direct evidence of an active subterranean ocean. Cassini flew through these plumes multiple times. Sampling their composition, analysis revealed not just water, but salts, organic molecules, and silica particles, hinting at hydrothermal processes at work deep within the ocean. Silica grains in particular are significant. On Earth, similar particles form when hot water interacts with rock at seafloor vents. Their presence on Enceladus suggests that the ocean floor could host hydrothermal systems, environments long suspected to be conducive to life. But Enceladus's ocean is not driven by the same mechanisms as Europa's? Yes, tidal heating plays a role. Gravitational interactions with Saturn and neighboring moons bend and flex the moon, generating internal heat. But the intensity and specific geology around the South Polar Tiger stripes indicate localized heating that could produce hotspots on the seafloor, potentially feeding chemical reactions and unique ecosystems. The organic molecules detected in the plumes include simple hydrocarbons and nitrogen-bearing compounds. These are not definitive signs of life, but they demonstrate that the raw chemical ingredients for biology are present. Add water, heat, and chemical gradients, and you have a recipe that on Earth supports diverse microbial ecosystems, especially around hydrothermal vents. Scientists estimate that Enceladus's ocean could be tens of kilometers deep and in direct contact with a rocky core. The ocean's chemistry appears alkaline, with a pH that on Earth would be hospitable to life. Furthermore, energy available from chemical disequilibria, differences in chemical potential, could fuel metabolisms even without sunlight. Unlike Europa, Enceladus provides a unique opportunity. Its plumes eject material directly into space. This means that future missions could sample ocean chemistry without drilling through ice. A spacecraft positioned in the plume field could look for specific biomarkers, chemical signatures that hint at life, such as particular ratios of organic molecules or isotopes that are difficult to produce abiotically. The certainty of an active alien ocean, coupled with organic chemistry and potential hydrothermal activity, makes Enceladus one of the most compelling targets in astrobiology. In the next sections, we will explore what conditions might support life and how scientists model possible ecosystems for these hidden seas. In the search for life beyond Earth, scientists often begin with three essential requirements: liquid water, energy, and chemical building blocks. on worlds like Europa and Enceladus. These conditions may be met in ways very different from Earth, offering a radically alien perspective on habitability. First, liquid water. Both moons host vast oceans beneath thick ice shells. Europa's ocean may be global and deep, while Enceladus's ocean, though smaller, is active and in communication with the surface through its plumes. Water is unique in its ability to dissolve and transport chemicals, acting as a solvent for potential biochemical reactions. Without water, life as we know it is extremely unlikely. With it, the possibilities expand. Second, energy. On Earth, sunlight drives photosynthesis, the basis of most ecosystems. But beneath alien ice, sunlight cannot penetrate. Instead, life would depend on alternative energy sources, tidal heating. In both moons, gravitational interactions with their parent planets generate internal heat. This heat keeps oceans from freezing solid and may power dynamic processes on the seafloor. Chemical energy. In places where water interacts with rock, chemical gradients form. On Earth, hydrothermal vents support diverse ecosystems independent of sunlight. Microbes convert minerals like hydrogen sulfide into usable energy through a process called chemosynthesis. Similar processes could occur on Europa or Enceladus if their oceans contact rocky cores heated by tidal forces, redox gradients. Life thrives on differences in chemical potential, where one molecule can donate electrons and another accepts them. These redox reactions are fundamental to metabolism. Alien oceans with dissolved chemicals from rock alteration could sustain such gradients, making life feasible even in perpetual darkness. Third, chemical ingredients. Cassini's plume analyses show that Enceladus has organic molecules, carbon-based compounds essential for building complex chemistry. Europa's surface ice also displays salts and organics mixed into fracture regions, hinting at a chemically rich ocean. Together with nitrogen, phosphorus, and other elements likely present, these form a chemical toolkit that life could use. Habitability also depends on stability. Oceans that remain liquid over geological timescales provide a sustained environment for life to emerge and evolve. Tidal heating on these moons acts as a long-lived internal furnace, potentially maintaining habitable conditions for millions or even billions of years, long enough for life to arise. Nonetheless, habitability does not guarantee life. The jump from chemistry to biology, abiogenesis, remains one of science's greatest mysteries. Scientists use Earth's extremophiles, organisms that thrive in boiling vents, deep crustal rocks, or frozen deserts, as models to understand how life might adapt to alien conditions. These extremophiles show that life can tolerate conditions far outside human norms, surviving near boiling acids, crushing pressures, or complete darkness. In Europa's deep ocean, life might resemble Earth's vent communities, microbial mats and chemosynthetic organisms clustered near hydrothermal activity. In Enceladus, plumes might carry tiny microbes or their chemical signatures into space, providing an accessible way to detect life without drilling through ice. But even in absence of biology, the mere presence of a habitable environment reshapes our understanding of where life can exist. Worlds orbiting distant stars, too cold for surface oceans, might harbor life beneath ice. Our definitions of habitable zones and life's limits expand with every new discovery. These hidden alien oceans challenge us to rethink the very concept of habitability, shedding light on possibilities that once seemed impossible. If alien oceans on Europa and Enceladus are habitable, what form might life take? To imagine extraterrestrial biology, scientists draw on principles from Earth's most extreme environments, where life continues in conditions once thought inhospitable and sometimes impossible. On Earth, hydrothermal vents along the ocean floor host rich ecosystems despite complete darkness. At these vents, mineral-rich water, heated by the planet's interior, supports chemosynthetic microbes. These tiny organisms convert chemical energy, not sunlight, into metabolic fuel. Tube forms, crustaceans, and complex food webs build around these microbial foundations. The key takeaway is simple. Life uses energy wherever it finds it, even in perpetual darkness, in alien oceans beneath ice. Similar mechanisms could exist. Europa and Enceladus likely have rocky interiors where water interacts with minerals. Tidal heating, gravitational flexing, ensures that conditions remain dynamic beneath the ice. In these subsurface seas, life might exploit chemical gradients as its primary energy source, just as vent life on Earth does when modeling potential alien life. Scientists consider 1. Microbial life first. Most models assume that life, if it exists, would be microbial, bacteria-like organisms or archaea. Simple, single-celled life forms are more likely to emerge in extreme environments than large multicellular beings. These microbes could cluster near hydrothermal vent analogs, utilizing chemicals like hydrogen, methane, or sulfides to fuel metabolism. 2. Biochemistry variations. Earth life uses water as a solvent and carbon-based molecules for structure and energy. Alien oceans also offer water and carbon compounds, as evidenced by plume analysis on Enceladus and ice chemistry on Europa. However, variations in ocean chemistry, salinity, pH, mineral content, could lead to life forms with biochemistries somewhat different from Earth's. Silicon-based compounds, unusual lipid structures, or alternative metabolic pathways might evolve. 3. Ecosystem structures. Rather than complex ecosystems like those near Earth's surface, alien ocean ecosystems might concentrate around energy sources, hydrothermal hotspots, chemical gradients, or mineral interfaces. Life could form layered communities where primary chemotrophs convert chemical energy, and other organisms feed off the byproducts. 4. Energy efficiency. In low-energy environments, survival may depend on extreme metabolic efficiency. Some Earth microbes can lie dormant for centuries or metabolize at rates near the thermodynamic minimum. Extrapolating this to alien oceans suggests life could be slow, resilient, and subtle, leaving weak biosignatures that are challenging to detect. 5. Biosignature possibilities. Identifying life remotely relies on detecting chemical signatures that are unlikely to arise from non-biological processes. For alien oceans, these might include unusual ratios of gases, complex organic molecules, or specific isotopic patterns. Cassini's detection of organics in Enceladus's plumes was a tantalizing hint, not proof of life, but proof that the chemical ingredients are present. Modeling such life requires bridging geochemistry, biology, and planetary science. Researchers use computer simulations, analog environments on Earth, like subglacial lakes in Antarctica, and laboratory experiments to explore how life could arise or persist. Yet scientists caution against projecting Earth life to literally onto alien oceans. Life might be fundamentally different in ways we do not yet conceive, but the core principles, utilization of available energy, adaptation to extreme conditions, chemical complexity, provide a scientific foundation for imagining life beneath ice. In many ways, modeling alien ocean life stretches our understanding of biology itself. It expands the definition of life's possibilities, encouraging us to look for subtle signs and to prepare for discoveries that might challenge our assumptions about biology and existence. The hidden oceans of Europa and Enceladus are compelling not just in theory, but in imminent reality. Several upcoming missions and proposed technologies aim to explore these alien water worlds directly, pushing the boundaries of planetary science and astrobiology. One of the most anticipated efforts is NASA's Europa Clipper. Scheduled for launch in the mid-2020s, Europa Clipper will orbit Jupiter and make dozens of close flybys of Europa, using ice-penetrating radar, spectrometers, and magnetometers to map the thickness of Europa's ice shell, characterize the composition of its ocean, and search for potential plumes erupting into space. By probing the ocean's depth, chemistry, and energy sources, Clipper promises an unprecedented look at one of the most Earth-like environments in the solar system. Meanwhile, the ESA's JUICE mission Jupiter ICY Moons Explorer will investigate Europa, Ganymede, and Callisto, Its suite of instruments will study subsurface oceans, surface features, and potential habitability. JUICE's long-term observations will complement Europa Clipper's focused approach, building a broader picture of Jupiter's icy moons. But perhaps the most exciting prospect is the idea of landing on these worlds. Concepts for landers and cryobots, robotic probes capable of melting through ice, are actively being studied. These could one day penetrate the ice shell and access the ocean directly, sampling water for signs of life. The technology is daunting. Europa's ice could be tens of kilometers thick, and power, communication, and contamination control all present immense challenges. Yet engineers and scientists continue to design systems, from autonomous submarines to ice-penetrating melt probes, that could one day reach alien seas. On Enceladus, the opportunity is slightly different because its plumes eject ocean material into space. Spacecraft need only fly through the plume to collect samples. Cassini already did this with great success, but a designated mission equipped with more sensitive instruments could analyze complex organic molecules, search for microfossils, or detect biosignatures in plume samples. This approach sidesteps the need to drill through ice, offering a direct window into the ocean below. Beyond these missions, advances in telescopes, like the James Webb Space Telescope and future observatories, allow scientists to study exoplanets with icy mantles and potential subsurface water. The lessons learned from Europa and Enceladus will inform the search for ocean worlds beyond our solar system, identifying signatures that hint at hidden seas beneath alien ice. Exploration of alien oceans is part science, part engineering, and part imagination. It requires global collaboration, decades of development, and a careful balance between ambition and caution, especially to avoid contaminating pristine environments with Earth microbes. But the potential payoff is enormous. Discovering life in an alien ocean, even microbial, would revolutionize biology, astrobiology, and our understanding of life's prevalence in the universe. It would confirm that life emerges wherever conditions allow, not just in the narrow habitable zone around stars. In the next decades, humanity may turn distant ice-covered moons from speculative curiosities into worlds we understand intimately. Their oceans could reveal chemistry, ecosystems, and perhaps even living organisms that challenge everything we know about life.